stopped recording.
Is that?
It just stopped recording.
Yeah, it froze again. I mean, it happened twice. I guess my laptop is dying. Okay, so now let's think about this, right? So here the basic setup is, hey, I just want to count how many words I've seen so far, right? But suppose, it's like I just want to see, maybe suppose it's some like client, okay? This guy comes and leaves later, right? Then it'll be more dynamic, right? Here the elements are only alike, but suppose elements can depart, right? Then maybe you want to say, hey, this element E1 comes, right? And later the element E1 disappears, right? You can also maybe you can even say, hey, element E1, it's like 3 copies of elements E1 alive, right? And then later one copy of element leaves. So there can be a more complicated model, more like a general model. But in this introduction to streaming algorithms, we are going to assume this vanilla model, okay, where we only select one element per time. Okay. So let's do the first example. This is a pretty simple example, but I think it's nice to think about. I think I can do this. So yeah. So I think I did this here, but let's just AI. I just write down some important notes here. Remember the AI is the I token in sigma, and M is stream length, and N is reference size, S is memory used. Okay, let's only remember this. Yeah, the first actually example is pretty nice. It's very simple, but it's very illustrative. So this is the problem. Okay. So if there is any element that appears more than half times pi. So by the way, fj is the I should define this. So basically, how many times J appears? Okay. So if some element J appears more than M over 2 times, M is the stream length. So at more than half of the times, if I see some element J, I want to output the element J, like the majority element. Otherwise, it's up and down. Is the problem clear? Okay. Yeah. Before we talk about the algorithm, how can you solve this, right? Or what's like easy way? So again, your goal is that you want to use you want to use the least memory, and you want to make, if possible, you want to make only one pass. How do you do this? It's not that obvious, right? Maybe you can maintain some elements for again. So, like one possible thing is that, okay, so initially you just maintain, you use like element 1, element 2, element 3, right? The element like M or 2. Like maybe but like, C, you have to maintain like, counter for each of these, right? Because you never know that which element will have like more than, will be the majority element, right? If like later, if like 1 appears again, right? Then this will become the majority element. If only 2 like appears later in the second phase, then 2 will be the majority element. So you want to keep like all these elements, right? Then you'll use M over 2, like memory, right? That's too much, right? I mean, anyway, it's not obvious. It's how you can solve this, right? So here is the algorithm. I'll just write down, the pseudocode, and then you'll see. I'll explain in words. Okay. It looks a bit like mysterious, so I'll explain words, and I'll give an illustration, and then explain what this means, okay? So let's see. So, okay. So sorry. Let's try to access, the generalize this, the frequent problem. So this becomes a frequent problem. Okay, so the only difference is that before majority was M over 2, that's the threshold. Now, in the frequent problem, if the frequency is more than M over K, I want to output all such elements. That's the only difference, right? So clearly, a frequency, is frequent. The frequent problem is generalized majority problem, right? Because when k equals 2, it becomes a majority problem, right? Let's try to solve this frequent problem. This is the algorithm for frequent problem. And I'm going to illustrate why this algorithm does something interesting. Let's say that k equals 3. Actually, I'm going to build the instance on the fly. Okay, so what do we do? Of course, we want to count, right? We want to maintain counter for element if possible, right? But we have to worry about how much memory we use. So I'm going to do the following for visualization. So like I'll just put down this 1, 2, 3, 4, 5. Like these are the elements from the universe. Okay. I'm not going to maintain these counters explicitly, but it's only for illustration. Okay. Like for in our thought process, let's say that we have like a 0 count for every element in the beginning. So I'm going to use this like a bar, unit bar, to indicate its frequency. So when I see this 1, when I see 1 here, right? Element 1 first. This is sequence error. I'm going to draw 1 bar here because it means a 1 count, right? Okay, then I see 2, so like 1 more here, and so I need to do better because it's otherwise it'll be very confusing. So 1, 2, 3, 4, 5, and then 3 here. So I see 2, so I add 1 more here. Okay, but of course I'm not doing it actually. Of course I'll put count 2 here, right? But it's just for visualization. And then when I see 3, this right. Okay, but now what do I do here? So now I see element 5, right? Then now I have 4 elements whose counter is non-zero, right? But I want to. My goal is to maintain a few number of counters. Okay, so actually, let's in this case, what do we do? Okay, so actually, I step 1 back here. Okay, so here, I saw 1, 2. Okay, so now I have so far I've seen 3 elements, right? I'm going to maintain I'm going to maintain at most 2 keys. Right? So then, okay, once I see 3, now I have counters for 3 elements, right? So what am I going to do? I'm going to conceptually raise the bar. Okay, so just like I raise the bar, so which means that I'm going to ignore that they don't exist. I can reset. I decrement count for everything. Okay, and then I see 2 now, and 3 now, 5 now. I think this is not very interesting example. So let's just do actually just 2, 3, and maybe like I see 2 here, 2, 3, and 5. Okay. Then I got 2, 3, and 2, 3, right? So far, I've only 2, right? 2 counters, right? But now I see 5, right? Then I have now 3 counters, right? Oh, bad. Okay, so I want to reduce it. So what do? I again reduce it or raise the bar. So this will be effectively gone. Right? That's what I'm doing here. So then, at the end, output keys with counter non-zero. That's what this algorithm does at the high level. Okay, there are some details, but is the algorithm clear? What I'm doing here? Right, very simple, right? Okay, good. Let's not worry about this how to implement this empty associated OA for now. But I assuming that you understand the algorithm clearly. Oh no, excuse me. So sorry. So I think. Sorry. Okay. So. Okay, this is not the algorithm for frequency, but we are going to use this as a building block, okay? And then lamp so I use this hat here because it's estimate, okay, to emphasize. So fj is without hat is true frequency, but hat means that it's frequent estimate. Okay. I want to see what's the quality of my estimating. Okay. The claim is the following. This is the claim. So at the end of the day, I mean, of course, I have an estimate, right? This is counter, right, at the end of the day. And that's my estimate, but I'm claiming that the counter can never exceed the real frequency. But but it cannot be too small. I mean, the difference can be at most m over k. That's a claim. Is the claim clear? Right? The algorithm is clear, right? Algorithm is clear and the claim is clear, right? But any questions about the claim itself? I didn't talk about the proof, but is the claim clear? Okay. This is why it's true. Let's first think about this, right? Fj. Here's two parts, right? The claim one, my estimate is no more than the actual frequency. So what happens here, right? Like, okay, so supposing that this is the end, right? I mean, the true counter is 3, right? F2 is 3, but my estimate was only 1, right?
Yes.
So like whenever whenever I raise the bar, my estimate will decrease, right? But I can never overestimate because I'm going to put the bar only when I see the element, right? So what's this, right? What is fj, right? Fj hat. This is like a number of j IC, right? Minus decrements, right? Number thresh. That's right. Number of J's IC minus number of threshold rays involving J, right? So, like obviously, I mean this, right? This number of J's IC is FJ, right? Of course, right? So this can be at most FJ, for sure. Agree?
Yes.
Okay. So the first part is almost trivial. Now let's think about the second part. Why is it true? I mean, so what I'm asking is this, right? We don't say that we don't decrement too many times. We don't raise the threshold too many times, right? So that how many times can I ever raise the threshold? When I raise the bar, how many like these bars do I delete? 3 here, right? Okay. So what happened here? Whenever I have 3 counters, right? Whenever I have k counters, I raise the bar threshold, right? Which means that I decrement the counter into the k, right? But what's total count? I mean, what is like this? What is this? This is obviously m, right? It's m. I'm sorry. Okay.
Yes.
This is m. So the total frequency, I mean, the sum of fi, sum of fj, right?
Yes,
This must be m,
Yes.
right? But whenever you raise the bar, like you are decreasing the frequency by k. So therefore, it means that this number, right? This number can be at most m over k, right? So this can happen, like you can raise the bar, like in the threshold only at most m over k times.
Yes.
Therefore, fj minus m over k, that's low bound of this estimate.